Let's take a look at an example how we can derive the standard electrode potential value. As previously explained, all these standard electrode potential value takes reference from the standard hydrogen electrode, which is defined by this half equation. And that is the reason why the standard electrode potential value is pegged at 0. Meaning to say, if we were to change the reference electrode, say for example, to use iodine and iodide as the reference electrode, which is now currently plus 0.54 volt. If we decide to use them as a reference electrode, then their values will become 0.00 volt. In this case, the half equation of H plus and your hydrogen would in fact be negative 0.54 volt, as the difference between the standard electrode potential value still remains to be 0.54, with the case of iodine and iodide being higher. Let's take a look at now how we can do an experimental setup to determine the standard electrode potential value of zinc 2 plus being reduced to form zinc, in order for us to quantify that the standard electrode potential value is negative 0.76 volt. So this is the setup that is required. The essential thing to bear in mind is that all the concentration of the ion has to be 1 mole per dm cube. In the case of any gas to be used, will be 1 bar. So in this case, since standard hydrogen electrode is being used, hydrogen gas needs to be at 1 bar. And we'll use platinum as the electrode, and the temperature needs to be 298 Kelvin. In the case of zinc, zinc needs to be the electrode, while zinc 2 plus needs to have a concentration of 1 mole per dm cube, while the concentration of H plus is also 1 mole per dm cube. And using the voltmeter that's connected to this electrochemical cell, we will be able to determine that the standard electrode potential value of Zn2 plus reducing to form zinc is negative 0.76 volt. We will also need to have a salt bridge, whether in electrochemical cell or in electrolytic cell. The purpose of the salt bridge is to ensure that they maintain net charge of 0 in each cell by allowing ion to flow between the two cells without extensive mixing of the solution. So typically, a salt bridge is made of aqueous ionic salts that must be good electrolyte. So for example, a lot of group 1 nitrates or group 1 salts which are soluble. So back to the example here of the purpose of the salt bridge. As the operation of the electrochemical cell proceeds, we know that zinc will be oxidized to form Zn2 plus, while in the other half cell, H plus is being converted to hydrogen gas, which means in this half cell, the concentration of zinc 2 plus is increasing. With the increase in the concentration of zinc 2 plus, we know the position of equilibrium will shift forward, which means it will increasingly become more difficult for zinc to oxidize to form Zn2 plus, if not for the presence of the salt bridge. The presence of the salt bridge would allow the Zn2 plus to migrate from the left half cell to the right half cell. So as the concentration of zinc 2 plus increase, we will know that in this half cell, you will now have more cation than anion. Conversely, in this half cell here, as H plus is being reduced to form hydrogen gas, you will find that you will have less cation than anion. Therefore, because of that, the positively charged cation, zinc 2 plus, will actually migrate up the salt bridge from the left half cell to the right half cell. If one Zn2 plus get into the salt bridge, 2K2 plus will be actually released to the right half cell in order to ensure that the salt bridge maintain the charge of net 0. So as time proceeds, the zinc 2 plus would have migrated from the left half cell to the right half cell. Conversely, there are more anion in the right half cell. Therefore, the anion like Cl minus would seek to migrate now from the right half cell to the left half cell. And in this case, when Cl minus get onto the salt bridge, given that the salt bridge comprises K plus and Cl minus, so the Cl minus on the salt bridge will be released into the left half cell. So in conclusion, as the operation of the chemical cell proceeds, you will find chloride present in the left half cell, while in the right half cell, you will find K plus and Zn2 plus present. In the operation of an electrolytic cell, the same could also be said. In this electrolysis, at the cathode, Cu2 plus is being reduced to form copper, while zinc is being oxidized to form Zn2 plus. And both solutions and the electrolyte here is your zinc sulfate, while the electrolyte in the right half cell is copper 2 sulfate. And the salt bridge is your sodium nitrate. So as the reaction proceeds at the anode, where zinc is oxidized to Zn2 plus, we know there will be more cation than anion in the left half cell. Therefore, because of that, zinc 2 plus will get on to the salt bridge. As a consequence, the Na plus from the salt bridge will be released to the right half cell. Conversely, we know that as copper 2 plus get reduced to form copper, the anion in the right half cell will be higher than the concentration of cation. Therefore, because of that, the sulfate will now migrate onto the salt bridge, and consequently, the nitrate will be released into the left half cell. Having completed explaining the salt bridge, we will now get on to calculate the standard cell potential. Take note that standard cell potential can be calculated for electrochemical cell or electric cell. They can also be used for calculations of redox reactions. So the formula to use for the calculation is E cell is equal to E reduction minus E oxidation. That could be used for electrochemical cell or redox reaction, or in the case specifically for electrochemical cell, we'll be using E cathode minus E anode. So let us take a look at an example. So these are the two half equations that we have. Clearly, in this case, the left-hand species of the half equation with a higher standard electrode potential value will undertake reduction, while the right-hand species of the lower standard electrode potential value will undertake oxidation. So in this case, Cu2 plus will reduce and stain will oxidize to form Sn2 plus. And the standard cell potential will now be 0.34 minus 0.14, giving rise to a standard cell potential value of 0.48 volt. If the cell potential is more than 0, it means that the chemical reaction is energetically feasible, thermodynamically spontaneous. However, it does not mean that kinetically it will definitely take place, because for that to occur, it depends on the activation energy. Finally, it is important to note that the standard cell potential calculation does not depend on the stoichiometric constant of the equations. Let us now take a look at redox reaction. In the case of magnet being an oxidizing agent, the question, one of the things to study is to examine who magnet can actually oxidize. Magnet's standard electrode potential value is plus 1.54, so it can actually oxidize chloride, given that chloride has a standard electrode potential value which is lower than 1.52. It can also oxidize bromide. It can also oxidize iodide as well. However, if we were to use acidified potassium dichromate, which is a weaker oxidizing agent than potassium magnet, because its standard electrode potential value is 1.33 volt, which is lower than the 1.52 volt, which is the standard electrode potential value for acidified magnet, then we can conclude to say that dichromate is only capable of oxidizing bromate, which is plus 1.07 volt, and as well as your iodide, which is 0.5 volt. However, it is not able to oxidize chloride, since chloride's standard electrode potential value is comparable or slightly higher than that of your dichromate. By calculating the standard cell potential, it allows us to conclude whether the redox reaction is energetically feasible or thermodynamically spontaneous. If the E cell value is less than 0, then the redox reaction is thermodynamically not feasible and not spontaneous.